My name is Michał Hermanowicz, and I represent the Interdisciplinary Center for Mathematical and Computational Modeling at the University of Warsaw. I work as a research and technical specialist in the application software and user support group here at ICM. It is my great pleasure to be hosting this session along with my colleague, Jarosław Skomiał, who works as a data center and network operations team manager. The presentation concerns supercomputing and the transcontinental ultrafast data transfer as a particular example of a project that ICM has been involved in. We will start with a bit of a general introduction to the topic, as well as an overview of some of the projects that we've been working on. And right after that, my colleague will continue on with the details for the second part of the presentation. So let me start with some of the background information about the ICM itself. It is a part of the University of Warsaw, which is the largest university in Poland, with 24 faculties and 30 academic and research units. The university dates back to 1816, and today we do have well over 40,000 students and 7,500 employees. ICM as a structural unit of the university and as an HPC center has been established in 1993, and what it does is it provides its users with both the high performance computing infrastructure as well as services that are crucial for conducting computational research in various fields of science. It is not, however, limited to academic projects, since we do also provide our services to some extent to businesses and to the public sector as well. There are four distinct areas of expertise that reflect our engagement in various projects, and these are data analysis, meaning processing of large volumes of complex data structures. There's education, and those educational activities range from HPC training to regular master degree program that we offer to our students. And now a large part of what we do is, of course, modeling and simulation, which refers to a wide variety of research initiatives and which is directly related to high performance computing, which is the key aspect of this presentation. Supercomputing itself is a very broad topic, which can be approached in a number of ways. What I'd like to begin with is the technological context, which is very often expressed in what we call the Moore's law. It is commonly used to reflect the fundamental limitations of the semiconductor-based or silicon-based, really, technology, and which is used to manufacture integrated circuits, or really the building blocks of modern electronic devices. Now, this is a very general trend which affects all sorts of computing devices, from the off-the-shelf consumer products to state-of-the-art supercomputers. As we approach the physical limitations, such as those related to miniaturization or related to a number of transistors that can fit within a unit space, then the technology changes to make room for progress. And so at some point we've had CPUs evolving into multi-core architectures to become a basis for modern computers, with practically very little change in the CPU clock frequencies, for example. The reason I'm referring to this architecture evolution is the fact that those multi-core designs became a major step towards increasing computer performance. And it is the performance and technology scaling that is of crucial importance when it comes to supercomputers. This process involves not just the hardware, but also simultaneously software solutions that are developed to ensure proper standardized communication schemes between the CPU cores, including mapping of the tasks and synchronizing data. Of course, programs that make use of such architectures and run in parallel is something that is not unique to what a supercomputer does. This can be done on a regular off-the-shelf desktop computer as well, and this is ensured by various standards involving software development tool chains, libraries, APIs, and etc. So what is it that distinguishes a supercomputer from a regular multi-core end-user desktop? It is not very strictly defined. What we usually have in mind where we when we refer to a supercomputer is that it is a class of computers achieving the highest performance given the contemporary technology. So in other words, at any given time, we do have a class of computing devices offering the highest achievable performance with the most advanced technology available. So those machines, as a result, exceed enormously the capabilities of regular computers, and so that's the super part. And the supercomputing of today relies very much on both multi-CPU as well as what we call multi-node architecture, so that we can have many computing units or nodes operating within the framework of a larger device. And those nodes are, of course, interconnected with the efficient network, which is the fundamental for the operation of the entire system. The programs that are executed on such machines have to be designed specifically to run within a hardware and software ecosystem to support certain operating systems, parallel programming models, and so on. Now, these parallel programming models do depend on the hardware architecture design, and let me just briefly address the shared and distributed memory systems that require a very different software approaches. So we can have a shared memory system where the CPU cores can access all the memory address space, and this is something that with some level of simplification, of course, happens within a single node of a computer cluster. So we can program applications like that, for example, within the OpenMP standard designed specifically for such shared memory architectures. Once we move on, however, from a single standalone computer node to a cluster of interconnected nodes, then we also need to deal with all sorts of problems of inter-node communication, data synchronization, and so on and so forth, which requires an entirely different approach, something that we can do with a message passing interface or MPI as an example. As I've already mentioned before, these architecture models are not unique to supercomputing because we can use those solutions on desktop computers as well. The difference, however, will be in the scale and in the resulting performance, which relies not just on the parameters of individual nodes, but also on the network, on fast and reliable storage systems, etc. On the other hand, it is, of course, technically possible to build a computer cluster with desktop components and a regular home network, such as the machines derived from the Beowulf project, so the Beowulf-like machines, which still, while not being a supercomputer, might be a reliable solution for some class of problems. So to move on to the actual HPC infrastructure that ICM offers, we do have two main machines in operation that are used for most of our research projects. One of those is the Cray XC40, named Okeanos, with more than 26,000 CPU cores in total, and with a single node having 24 cores and 128 gigabytes of RAM. The other machine is a Huawei cluster called Topola, with more than 6,000 CPU cores in total, and with a single node equipped with 28 cores and either 64 or 128 gigabytes of RAM, depending on the user's requirements. These computers are involved in most of the projects here at ICM, and apart from this hardware architecture, however, we do also provide other services, including complex research and technical user support. Most components of ICM's infrastructure are located in our newest data center in Warsaw, built in 2015 and called the Technology Center. It has a 4 megawatt power line and has the total of 2 petaflops of computing power and the total of 25 petabytes of storage space. Now, among the variety of research projects that we work on, I would like to briefly list and highlight those of particular importance. This list is not a complete one. It does, however, give an idea of the kind of problems that are solved with our supercomputers. The numerical weather portal certainly belongs to the very well-known services provided by ICM. It is hosted at meteo.pl website, and the weather predictions up to 120 hours in advance are calculated within the unified model and published regularly online. The service has been established nearly 27 years ago and is used by the public sector, by the researchers, and as well as commercial entities. One of the younger initiatives, on the other hand, is the ICM's epidemiological model, which has been successfully used to describe the spread of the COVID-19 pandemic in Poland. So the model works at the nationwide level, and it provides both the short-term predictions as well as the potential long-term variants of the pandemic development, also taking into account the administrative restrictions that are being imposed in the country. The ICM researchers working on the model do cooperate closely with the Ministry of Health and with the RCB, which is the Government Center for Security. The project is hosted at covid19.icm.edu.pl website for those who would be interested in the computational details. Other projects include GATO, which stands for Global Air Transport Optimizer. This one is a joint undertaking of ICM and International Civil Aviation Organization. It is a state-of-the-art aviation analytics system which operates on an integrated repository of air traffic data to allow for its planning and optimization. Apart from those projects that are strictly computational in nature, ICM also does play an important role in providing Polish researchers with scientific literature within the project known as the Virtual Library of Science. The literature includes over 26,000 journal titles and over 150,000 books. This database is used by over 500 national institutions on a daily basis. Now, the computational examples that I've listed, they do show how this potential of supercomputing facility can be used. There are, however, other initiatives and other projects, such as conferences, most notably the Supercomputing Frontiers Europe, as well as educational and training activities. It is worth mentioning that apart from the traditional HPC resources described earlier, we do have a number of experimental systems that are used for small-scale research and development projects. One such system is the NECSX Aurora Tsubasa vector computer, which is used mainly for software development, software vectorization, as well as for innovative approaches to solving challenging problems in the domain of material science and artificial intelligence. Vector computing has been present in the development of supercomputers since the 1970s, so the idea is certainly not new. In the early days, those machines have been standalone units controlled by dedicated operating systems, and this modern design that we have in ICM is basically an accelerator in the form of a PCI Express card called a vector engine and hosted by a standard x86 64-bit server. One example of a problem that we've been solving with this particular vector computer has to do with quantum physics and the electronic structure calculation of solid-state systems in the nanoscale. In this particular example, it is the titanium dioxide. This example comes from the domain of material science, and this kind of calculations enable us to predict the properties of a material as a function of various structural defects, for example, or other factors. The important aspect of this particular project is the scale of the system that is being described. The model consisted of nearly 250 million atoms, and it has been solved efficiently with just 8 vector engines communicating via a message passing interface. Such a large system would be practically impossible to describe in other well-established computational approaches. This project was also the topic of the master degree thesis of one of the ICM students within our master degree program in computational engineering. The resulting software package optimized for the modern vector computer architecture was published as free software and is available in the ICM's public code repository, and it is also referenced in the paper published in the Computer Physics Communications Journal. The software is sort of a framework that, and a benchmark as well, that is intended to be a basis to build upon and to extend to other systems and other properties. It is also an example of a problem that is very well suited for supercomputers because of the complex mathematical description of materials in the nanoscale. Let me briefly summarize this introductory part of the presentation by saying that it is in fact rather a highlight of our diverse activities. It does, however, serve as a context in which we can now move to the main topic, which is the transcontinental ultrafast data transfer. So I will now hand over to my colleague, Jarosław Skomiał. Thank you very much indeed.
Okay, thank you, Michał. Now we can proceed to the networking part of this presentation. As you can see on this simple drawing, there are 3 main components of an HPC system. So we have a user, computation nodes with software on it, and of course, storage with data. Everything is connected with high bandwidth network. But if we go deeper, we can realize that computation nodes have a separate network for management and for orchestration. There is a separate network for storage. So it gets more and more complicated when you go deeper in this infrastructure. Of course, in HPC networking, we want to provide the highest bandwidth and the lowest possible latency. Of course, with proper level of resiliency and scalability, and at reasonable cost. So that's why we have our own fiber network at ICM to connect between our both data centers. It's 25 kilometers from each other, and we have 200 gig interconnection between them. But if we want to go further to operate on the country level, there is Pioneer National Research and Educational Network in Poland. It's 7,500 of fiber network between main academic cities in Poland. We are connected to Ghent and CERN. Also, we are connected to Amsterdam, London, and Frankfurt Internet Exchange points. Everything is operated by Poznań Supercomputing Center. And If this is not enough, we can still operate on a European level thanks to GEANT network. And then we can use the GLIF. It's a global lambda exchange network that we can use to connect to other research institutions worldwide. This infrastructure was used 2 years ago to provide to run a project with ICM and A-Star CRC from Singapore and Zetar Corporation to provide a 100 gig link from Poland to Singapore. It's a great result because the distance between both countries is 20,000 kilometers, and for this project we used just regular hardware. Of course, together with infrastructure like computation nodes and fibers, we need team of hardworking people who can run this project. So we have a team of 3 people from ICM, 5 people from A-Star CNC, and of course Zetar team who supported us with software that we used. Altogether, we were supported by Pioneer, GEANT, and Singaren network. The hardware that we used for this project was just a regular hardware that we can find in our data center. So it was 2 years old servers with Xeon CPUs, 192 gigs of RAM, and 100 gig Ethernet cards. As storage, we used Lustre storage on 40 servers. Altogether, it was almost 1 petabyte of storage. In A-Star CRC side, we had just 1 data transfer node with NVMe storage. As a result, we achieved 60 gigabits on 20,000 kilometers distance. The preparation time of this project was no more than 2 weeks, which makes it really fast for such a infrastructure and big team. Zetar ZX software was very good tool to provide connectivity on such distance and for this to achieve this goal. The hardware that we used for this project was really modest, and it wasn't top of the shelf hardware. With this infrastructure, we can move 1 petabyte of storage in less than 2 days. The impact of this project was to show that we can learn how to transfer and store and compute data, because actually data is oil of modern digital age. We can run environment of worldwide distributed HPC centers which provide in a different manner computation nodes or storage infrastructure. Long distance data transfer and computation is possible for research units. And of course, separation of storage and computation nodes, it's not a problem in these days. We met quite good recognition of our projects, which was presented in multiple branch portals. Also, it was presented on Supercomputing 2019 conference. It wasn't just one network-oriented activity in HPC environment, because in 2019 we also collaborated with Infinera Corporation, and we tested the solution to transfer 1.2 terabit on a short distance of 25 kilometers. Also, we are engaged in DTN infrastructure worldwide. It started in 2017, and we still operate the DTN in our data center. The other project also started in 2017. We joined a global research platform with our data transfer node. which helped us to understand and learn how to transfer data between different parties of this network. One of our newest activity in the network world is joining SciNet network. In this society, we provide our virtual lab, and also we are active members of supercomputing conference. Our last activity in networking was joining Data Mover Challenge as infrastructure provider. In this society, almost 20 research units from all over the world provide 100 gig connection between each other, and different research units and teams can test their solutions to transfer fast data. Okay, I think that's it for our presentation. You are very welcome to visit our website, and we are always very open to collaborate in different HPC-oriented areas. Yes, thank you so much for attending this presentation. Also, would like to say thank you to Polish Investment and Trade Agency for having us here.